All right, let's get started, right? So it's not a news today that we are living in a data-centric world, right? So everything around us is constantly generating large amount of data, which is being stored, processed, and analyzed in some sort of cloud environment, using popular frameworks like Hadoop, Spark, Hive, or Flink, right? So these are all data-intensive frameworks which routinely analyze terabytes of data every day. They usually run on hundreds to thousands of machines in a distributed environment. And naturally, their performance depends upon both the performance of the networking infrastructure you have as well as the storage where the data is being stored, right? So specifically the last point, so if you have a look exactly what has been going on in the networking and storage area, so luckily in the last 10 years or so, right, networking technology has improved consistently from 1 to 10 to 40, now 100 gigabits per second, right? And at the same time, there's a large amount of related work and literature which has been constantly trying to optimize the performance of the network, right? So once the data is ready, how efficiently can you transfer it over the network to the other side? There's a bunch of references, you're not supposed to read them, but just to get the idea that there's a large body of work which is done in optimizing the networking performance. At the same time in storage, right, we have seen the emergence of non-volatile memories in enterprise computing, right? So we started with SSDs, now we have a next generation of solid-state drive with NVMe, better interfaces, high performance, and endurance, and different type of things you can do with them. And naturally in this area as well, you have a large body of effort that has been put in order to deliver the great performance that you have in the storage to the application that are running on the server, right? But at the same time, there's a growing gap between what you can get out of storage and what you put on the network if you have a network storage application, right? So we know in the best possible way how to get data from your local solid state storage to your server, something in between, and then we know how to put it out in the network in the best possible way. But how do you put those two things together? That's the focus of this paper. And at the same time, we have to remember the CPUs are not getting faster, right? Between the order of magnitude performance improvement that we have seen with the devices, CPUs is still the 3 gigahertz CPU that we have almost a decade ago. So what all of this means, so what is the cost of this gap that has been growing, right? So here are some numbers. So on the x-axis, we have various configuration or popular ways in which the data is served over the network, right? On the y-axis, we have thousands of IOPS that we observe to serve 4 kilobyte page from the flash. So the first one is the specification that the device we have, NVMe device, what is the specification says. Then we measure the block IO, right? So the three devices that we have, we effectively had 1.2 million IOPS that we can deliver for a local FIO test that we did on our server, right? So this is all good. This is very close to what we are expecting to get. But as we move our clients across the network to the other side, so using NetPerf, which is a popular networking benchmark, we extended it to read and write to the storage as well. Then you have iSCSI, right? Then you have a key value store. Then you have NFS. Then you have HDFS configuration, which are all trying to serve data over the network. The performance is lost essentially, and the networking applications that are running in a distributed environment, they are not getting the full benefit of the raw hardware performance that you are supposed to get from your hardware that you have in the system. And by the way, since we had a discussion yesterday, I'm obliged to point out that the error bars for these numbers are in the paper, but they're just not shown here. So what is the reason behind the gap that we see in the performance, right? So conceptually speaking, logically what is happening in these experiments is that you have a client over the network which is sending a request to a server in between to serve some data from the storage. Server is doing a local storage IO and sending a response back, right? So logically, the performance that you're supposed to see is the sum of your networking performance, your server time, and the storage IO, right? And the raw networking and raw storage, we know we can do very, very well, right? So it's the server time which is of interest to us. What exactly is happening in that server time which is running on your CPU, right? So naturally it involves application, it involves scheduling, it involves FS lookups and various other overheads that we are going to analyze, right? So what happens when the request comes in, right? A network packet comes in, it gets through, you have an interrupt, you have a software queue, TCP/IP processing happening, then application is scheduled, application receives the request in the user space, application, oh, I have to serve the data from the file, right, which is on the local file system. It schedules a request to the file system, there's a file system is involved, there's a translation, there's a permission check, there's an extend lookup, and the file system will queue up a block IO to the flash device. The IO will finish, again, the data flows backward to the user space, and the application is involved in scheduling a transmission, right? That goes back, and then the TX is done, right? This is kind of interesting, what happens when you're trying to serve a network request. And obviously there's a optimization here that you can use a send file to not pull all the data in the user space, right? But that still leaves this unnecessary application and operating system and the file system involvement in your data flow, that you have to involve application to ask, oh, where exactly this is stored, how can I transmit it, how can I access it, right? And this is exactly what we are after. How can we reduce this overhead which is involved in every request that we are serving, right? So what do we propose? So we propose to eliminate application involvement. We propose to reduce file system overhead, so that you don't have to involve file system in each request. And we propose that our network controllers and our storage controllers are smart enough, given the right set of abstraction, they can talk directly to each other in order to serve the data from the storage over to the network. And how do we do this? We propose to use RDMA, which is a popular high-performance networking technology, which is finding increasingly many applications in commodity data processing system these days, right? The general idea is that you separate your data and the control path in your application. So all the abstraction and the resources are pre-allocated before the data transfer starts. And when the data transfer starts, it's done at the speed of the hardware, right? So this is the general high-level idea of RDMA. We have designed and implemented a new file system, which is called config.fs, which supports a very simple file layouts, right? So there is no fragmentation, there is no extend. All the files are contiguous. You can calculate exactly where it starts, where it finishes, and what is the addresses in between when you have to transfer, right? And we use virtual memory as an abstraction or as a first-class identifier to the blocks which a network is supposed to transfer from the storage. And once you put these things together, so this is how the FlashNet's read path look like, right? So as the request comes in, you have a local RDMA processing, right? And from that processing, we figure out exactly the address they are supposed to transfer, how does it map to a local block address which is on the flash, and the request to the flash is immediately issued in the software queue. There is no scheduling point in between, right? Once the request comes in, we have possibly a scheduling point there, and the response is prepared and data is transmitted immediately. So there's no application involvement, there's no file system involvement in doing the processing of this whole pipeline. So how do we do that? So obviously we have a flash controller that we have implemented in software, right? It manages a bunch of flash drives, you can see in the corner there. It virtualizes those flash drive and give an abstraction of 64-bit contiguous logical block address space. It also has a shared DRAM pool, which is responsible for managing IO requests and various other responsibilities. Detail of this are discussed in the paper, right? But the key thing to notice is that it virtualizes flash and gives an illusion of a 64-bit LBA space, right? So on top of which, our file system, contiguous file system, allocates and deallocate files. So since you have a large virtual address space, you can essentially allocate a file, whatever size you want, and it's contiguous in the space, right? And obviously, you can ask what happens if you grow and shrink, then just remap the mapping of the file in that address space. You don't have to actually move the data. There's various techniques to do these tricks. And the file system is responsible for supporting mmap and local file IO on the device, right? Then we have a RDMA controller, which is also implemented in software. All these things are essentially kernel modules you can insert without modifying any of the Linux kernel code. RDMA controller is responsible for lazy pinning RDMA resources, right? So one of the key things with the RDMA technology is that all the buffers that are involved in the transfer, they are pre-allocated and pre-pinned. So if you're trying to transfer a terabyte of memory, you have to pin the terabyte of memory, which is not what we want, because that could be really the size of the data you're trying to transfer from the flash. So instead, what it does is that when you try to register your memory, okay, where does that memory come from? It's a memory that you get from the mmap. So you mmap the files which are on config.fs into your address space. You get a virtual address. You register that virtual address to the RDMA controller, which just makes a note. Okay, I understand you're trying to register this thing, but I'm not going to allocate any pages. I'm not going to pin anything. We'll see about that later. And it is responsible for processing your RDMA requests when they come in, and RDMA requests usually have a virtual address, what they want to read and write. And it then translates that virtual address into a flash block address and talk directly to the flash controller. So in a sense, all these three components, what we call FlashNet stack. They are jointly optimized and designed in order to serve your network data at the best possible performance that we have. So if you put an application on top of that, that's essentially how it looks like. So the application is responsible for unmapping the files from the config.fs. So at that point in time, your file can be translated to a logical block address to a physical block address, and this part from here to here is managed by the config.fs. From here to here is managed by the flash controller. This part is managed by the RDMA controller, because this is where you do the memory registration and you get an S tag that you distribute to your clients. So this is the extended control part that we have in the FlashNet stack. And once you're trying to serve the data and access the data, the flash controller and RDMA controller talk directly to each other from the S tag to the LBA address, because the RDMA controller knows that your files are contiguous. So whatever virtual address it has, it can just add the offset and it will get the logical block address, because they both are contiguous. And since the traffic which is leaving the controller here is RDMA traffic, which means that we can deposit this data directly into the client buffer without having to leave it in the network buffer or iSCSI buffer or an NFS buffer on the client side, right? So this is also a very important distinction, that the clients here, they are your usual unmodified RDMA clients. They don't have to know, and they don't have to know where the data is coming from. Data might be coming from the DRAM, or data might be coming from flash. So from the client point of view, it's absolutely transparent. Client just have to program RDMA. That's about it. All right. So there's of course a lot more details which are discussed in the paper. Please, I encourage you to have a look there. So briefly in the evaluation, I'm trying to answer two questions. So how efficient is the IO path that I have shown you so far? And does it help with application performance, right? So we have a cluster of 9 machines with dual socket CPUs, 40 gig networking, and NVMe flash. And the peak performance of those devices are around 6 gigabit per second, 2.7 gigabyte per second for the write, and 1.3 million IOPS. That's essentially the peak that you saw in the figure in the beginning of the presentation. So here's the IO efficiency numbers, right? So on the x-axis, we have number of clients that we are increasing from 1 to 256. And on the y-axis, we have amount of IOPS which is served by the system, right? We are presenting the number for the socket and file, which was the best possible configuration we can find in the beginning. And we compare it with the FlashNet. So in the usual case of socket and file with the net perf clients, that saturates around 850K IOPS. At this point, the CPU is fully saturated. It cannot serve any more capacity. Whereas the FlashNet essentially delivers close to 1.3 million IOPS that you're supposed to get from this configuration. And at this point in time, actually, since our configuration is in a way that the storage and network are balanced, at this point in time, essentially our 40 gig NIC is saturated, right? So if you have more NIC or if you have more storage, we hope that we will be able to drive more capacity given our configuration. How does it help with the applications? Well, we have developed two applications. One we wrote from scratch, which is a key value store. Other one we ported an already existing RDMA application, which is a distributed in-memory store, and its application, which was a distributed sorting, essentially a terasort, right? Number for the terasorts are in the paper, but I'm going to discuss a little bit more about the key value store. So here we compare the performance of the key value store with the Aerospike, which is a well-known key value store. The difference between Aerospike and in-memory key value store is essentially that the metadata that the key value stores, it's able to spill it over to the storage, right? So your amount of data that you can store in your key value is not limited by the amount of memory you have. So we have Aerospike, then we have implementation of our key value on the sockets and files, and the same implementation that uses FlashNet's RDMA operation to read and write data. So here we show you the performance with the get and put. So naturally, FlashNet and so first of all, the first thing to observe is that between Aerospike and normal implementation, there's already some performance gain. And between the socket and file, and when you use FlashNet, especially for the gets, we get between 3.2 to 1.8x performance improvements. And obviously, the write performance is a little bit more limited by the write performance of our drives, which in case we that's why you don't see much gap between here. But for the get, absolutely, because of the efficient RDMA reads, you have a very close to the networking performance that you have, and we deliver almost 3.8 times performance improvements. So there are more details in the paper, but to conclude, what the key problem that we are trying to solve is that we have identified that the way currently the data is served over the network from the high performance storage with the combination of high performance storage and networking is not efficient. This can be improved by applying the RDMA principles, which is a path separation that you allocate all the abstraction and resources beforehand. And when the data is transmitted and accessed, you don't involve any slow operation, and you can transmit at the speed of the hardware. We extend this basic principle that is used in the networking to include storage. That means include a file system and include a flash controller. FlashNet is a concrete implementation of this idea, and we have demonstrated its capability in the micro benchmarks as well as a set of applications. And we are in the process of open sourcing what we have built so far, and we are very excited to explore more possibilities, what kind of new applications can be built using our stack that we have presented so far. Thank you very much for your attention.
We did something about 10 years ago more specific for block storage. The idea was to have a RAID controller where the parity groups go across boxes. So if the box fails, the drive, you don't die. And there we extended iSCSI to permit what we call third-party transfers when the controller can instruct one box to direct the RDMA to another box. So the traffic moved directly, and you still have a nice coherent central control.
Right.
Scaled beautifully. So it's a more specific instantiation of this kind of thing.
Right. So what was the project called?
We call it TPT RAID, third-party transfer RAID.
Okay. Sorry, I'm not. But the work essentially is also more parallel to the NVMe effort recently, right? So
yeah, we did something very narrow for that to demonstrate.
So difference with that would be like, for example, the figure I showed, right? With the iSCSI NFS, so the data comes in, that stops here, right? So the application has to pull from the block layer here.
Yeah, we stayed below the file system just to show RAID control.
Right. So,
in FlashNet, what did you find to be the bottlenecks to when you hit those numbers?
I think it was CPU. I think because it is a software implementation, right? I did point out CPU is a bottleneck, but the general idea is that what you use your CPU for, right? You have to be more careful what type of processing you want to do, right? If your end-to-end latencies and bandwidths are in microseconds, you don't want to do 10 microsecond buffer allocation in between, right? So, and with the RDMA concept, you can actually move those two things separately, and you can do allocation separate and the data transfer separate, right? But still, there's some CPU which is involved here. So, the idea is that once this is mature, and the APIs are more mature, right? Because you also have to find the right set of APIs that these three components use, right? So it's all asynchronous. There's no blocking point, and it's more equivalent to the IX operating system paper from OSDI, that once the thing comes in, it just goes through as fast as possible.
How many SSDs were in your experiments?
3. Yeah, that's what we
scale it further.
Sorry?
Do you think you'll be able to scale it further?
Yes, we are trying to set up a new infrastructure where we have kind of 100 gig networking and more SSDs per box, and then we try to see what kind of performance we can deliver in that case.
Hi. Does FlashNet actually need its own file system, config.fs? And if it does, why? What certain aspects of config.fs are actually essential for the system?
So, okay, yes, FlashNet needs config.fs because the translation or the basic assumption that the kind of calculation the network controller does assumes that the file are contiguous and the offset it can calculate by just adding and subtracting, right? The offset it's getting. So it requires config.fs. But having said that, config.fs from the user point of view is no different. It's just a general POSIX implementation. It hooks up in the BFS layer. And you see just absolutely no differences. The only thing I can think which we have not evaluated in this paper, which is kind of known to be an issue with the virtualized file system, is that at some point in time, after long run, right, after resizing and remapping your files, at some point in time you have to do garbage collection and you have to remap and rearrange your virtual address space, right? But
I see. But because we are still in, let's say, the data path still goes, the control path still goes through the kernel space. So actually, I thought, for example, you could find the LBAs, let's say from X4, and then transfer them with a NIC directly to the client, without having your own file system. Have you tried that? Or,
right, but that essentially will involve, because RDMA controller doesn't know what would be the LBA. It has to talk to file system, right? And it depends on how large your file is, how many extents are involved, right? That translation could be expensive. So we have a breakdown in the paper where we show that. How much, actually, I might have it here as well. Right here, yeah. So this is with the socket and file, the 7.3, right? So this involves the translation that the file system and the rest of the storage stack is doing. And this is our, which is just showing the block IO at the end of the line, right? So you see the difference between that. Yeah. Sure.
I don't really get this work.
Sure.
What I think the performance that you've shown us is config.fs versus X whatever.
Mm-hmm.
Right? That's what I think you've shown us. But I already know that config.fs is better because others have shown it. And I think that you can actually put there any other file system,
Mm-hmm.
so long as you can handle the page.
Yes.
But that's the only place, if I'm not mistaken, that you've used
Right. So
the fact that it's contiguous on the page, right?
I agree, and I think there was.
So if I'm able to handle the page fault, if the device is built in this way, that it can sustain, tolerate the page.
Right.
Why should I entangle the both of the mechanisms? I can use whichever file system I want.
Right, and
If
there's
there's a page fault, let the file system handle it. And that's that.
right. I agree, and I think there's an SPLOS paper this year which essentially is about lazy pinning and handling the page fault with the network controller, right?
But by the way, NICs nowadays, RDMA,
Yes, they can do
they
that.
support page faults.
Right, I agree. And
The only problem you have is the way to verify the consistency of these stats.
sorry.
With the current page fault mechanisms.
Could you please?
Right. So I agree. So, but the difference is still would be that to handle those page faults, right, you have to involve the file system to do the translation, right? So there's one difference. And the second difference is that I haven't talked about is that because your flash controller and the RDMA controller are talking to each other, flash controller has information about the access pattern and the heatness of the page and LBA, and which information is actually used to better manage flash. So if you are issuing all the RDMA requests that comes in immediately to the flash, then you're going to burn out the particular block that is there. But in our case, essentially this information is shared, and we use this information to essentially use a better where labeling on the flash, which.
But you didn't demonstrate this benefit. What you've demonstrated is the difference between the performance of two different, completely different file systems.
Yeah, so the way learning, I
If
think,
you
or
want to demonstrate that, you would have used the same file system.
right, I agree with that, but then we use the same file system in the key value evaluation, right? So in the key value evaluation, the second is our contiguous. It's not running on ext3, or sorry, ext4. But I agree with the general criticism that yes, in order to show the gap between what we have demonstrated and what could have been done, right? So if ext4, let's say the trick between using the contiguous files is that we make the translation just dumb, right? It's just the offset calculation, that's about it. And the cost that the general purpose file system usually have to pay in order to do so, right? So that's not trivial, right? And we could go and modify, I agree with you, and redo the experiments, but let's say with our limited time budget, this is what we came up with, right? And we wanted to have, let's say, more control over, because the file system is not just about the file management, it's also, there's a kind of a centralized buffer pool which is shared between the file controller, the RDMA controller, and the flash controller, right? And
I agree with
So
you.
let's,
These are
I'm
claims.
sorry, I have to interrupt.
These are claims which are not proved.
We're running out of time. Please.
sure, I accept that criticism.
Yeah, we can continue discussion offline, but we don't have time, around time, so we'll have to move to the next